Hey guys, welcome back to another video. So in this video, I'm going to be talking about ice charts. Ice charts are super important for equilibrium problems, and it's like a really good pictorial representation for finding like equilibrium concentrations for like products or reactants in an equilibrium problem. So I'm first going to be going over like sort of a few examples, and then I'll sort of tie in some like last principles, and that should be like a good start, just for learning ice charts in the beginning. Okay, so for this first example, we're given 4 moles of HI, and it's placed in an evacuated flask, 5 liters. What will the equilibrium concentration be? So the first step obviously is I'd like to convert this into molarity, so moles over liters, which is 0.8 molarity. 0.8 molarity. That's a nice table. And for hydrogen and iodine, there's no concentration. We just have HI, so we can say this is 0 molarity for both. So we just have reactants. Now, a really important starting place for any ice chart is to calculate Q. So Q is nothing but Q is the reactant coefficient, and it tells us whether the reaction is gonna go right or left, and we need to know this to make our ice chart truly like work. So we can do that by just using the initial concentrations. That's what a reaction quotient is. So it's just 0 times 0 divided by 0.8 squared, which is 0. And because Q, which equals 0, is less than 0.016, or the equilibrium constant, then the reaction will go right. So this reaction will go right. Now, probably the most important part, the change. The C counts. The C stands for change. Now, the thing about C is we don't know by how much it actually changes, so we have to use a variable x. Because this thing goes right, we can say you can subtract 2 times x, because there's a coefficient here. Because the reaction is going right, we know the reactants are being consumed and products are being made. So reactants HI are being consumed and H2 and I2 are being made. So we can say plus x, because it has 1 as its coefficient. So essentially this is what we're getting. We're getting 0.8 minus 2x, x and x. So these are our equilibrium concentrations. Now we want to know what x is so that we can actually get the real number. So this is what we get based on what the definition of an equilibrium constant, or equilibrium constant. Yes, we get x times x, right? X and x, divided by 0.8 minus 2x squared. And this equals 0.016. Now we just need to find x. And this is sort of like a tedious way to do it, but we need to be able to find it. But we have squared on both on the numerator and denominator, right? So we have like x squared divided by 0.8 minus 2x whole squared. So what I do, especially, what's the smart thing to do is actually to square root both sides. Then we're left with just x to the 1, and then we can rearrange it and get x. And what I get is x equals about 0.081 slash 0.0808. So now that we have x, we can get the actual equilibrium concentration, which is this, right? So here, I'm gonna erase something. I'll just erase this stuff. So now that we know what x is, we can get the actual equilibrium concentration. Okay. Yeah. And 0.8 minus 2 times 0.081 equals about 0.638, and this is the hydrogen iodide concentration. So we have another example right here. It says find the equilibrium concentrations for this reaction, and you have 0.05 moles of each species in a 2.5 liter. Oops, that's meant to say flask. Yeah. Okay. So first what I'd do is I'd find each species in molarity, and that's N over V, which equals 0.05 divided by 2.5, which is equal to 0.02. And it's for each species, so I would do this. Again, the first step I'd do for any of this is to find the reaction quotient Q, because finding Q will tell us which way the reaction goes, right or left. And that's nothing, that's just 0.02 squared divided by 0.02, which equals 0.02, and 0.02, which equals Q, is greater than Kc, which is this. So this tells us that the reaction actually, it goes left. Now, if we literally just looked at this without calculating Q, we probably would have assumed left to right, but it actually goes right to left. So what this tells us actually is that these compounds are being consumed and these are being produced, right? So minus x plus x 0.02 plus x 0.02 minus x 0.02 minus x. So now that we have our equilibrium concentrations, we can do this. Plus x, and this equals 9.32 times 10 to the negative 3. Now this part will be really, really dirty. We can't do the square, we can't square root both sides, just because this problem isn't like that. This isn't squared, the denominator isn't squared, so we can't really do that. What we have to do is rearrange this into a quadratic equation and use the quadratic formula. So I'm gonna erase some stuff, and we should probably do that. Yeah, this part's really sort of tedious, but it's what must be done to find x. Once we find x, we should be able to get each concentration. So basically, let us rearrange this. Okay, so we're given this, right? So let's rearrange this. So let's multiply 9.32 times 10 to the negative 3 with this. And so what we get is 1.364 times 10 to the negative 4 plus 9.32 times 10 to the negative 3x. I'll make that more noticeable. And you equate that to this whole thing squared. And I'm just going to do that right now. So that's going to be 0.0004 minus 0.04x plus x squared. Now we combine like terms, and what we get is x squared minus 0.04932x plus 2.136 times 10 to the negative 4. So using quadratic formula, we can just so a is equal to 1, right? Because this is our coefficient. B is equal to 0.04932. C is equal to 2.136 e negative 4. So now we have to use quadratic formula, which is negative b plus or minus square root of b squared minus 4ac over 2a. And when we sub in a, b, and c, we get x as equal to 0.0445 or 0.0048. So obviously it can't be both answers because that makes no sense. So let's try this one. We have to figure out which one's extraneous. So if we plug in x as 0.0445, let's say for something like this, we get a concentration that's negative, right? Because 0.02 is more than 0.0445. 0.02 is less than 0.0445. So we get this as a negative answer, and because of that, this just doesn't make sense. So x is essentially 0.0048. Yeah, so once we find x, we can find each equilibrium concentration. So let me erase everything. Okay, yeah. So the concentration of Cl2 equals the concentration of PCl3, right? Because of these equilibrium concentrations, and equals 0.02 minus 0.0048, and concentration of PCl5 is equal to 0.02 plus 0.0048. All right, that'll be the end of the video. Thanks so much for watching. I'll see you in the next one.